Welcome back to Upgrade to General, a series to help you upgrade your amateur radio license to general class. This episode is sub-element G5, question group A, about electrical principles, specifically reactance, inductance, capacitance, impedance transformation, and resonance. I'm your host, Ron Call, KE7CR. Let's jump right in. Question 1 asks, what happens when inductive and capacitive reactance are equal in a series LC circuit? L is the symbol used for inductance, C for capacitance. So a LC circuit means it has both inductance and capacitance. When you have an inductor or a coil, it generates a magnetic field and stores energy in a magnetic field. Capacitors store energy in electric fields. In a circuit where you have both inductors and capacitors, they're going to have some opposition to the current flowing. Instead of calling that opposition resistance, because it doesn't actually convert the energy into heat, it converts the energy into a magnetic field or an electric field. So we're going to call that opposition to current flow impedance. Impedance is a combination of the opposition caused by the inductance and the capacitance. Specifically, we call the opposition to current flow caused by an inductor or a capacitor reactance. That opposition is a reactance to current flowing. Now, if it's caused by the inductance, we call it inductive reactance. If it's caused by the capacitor, it's capacitive reactance. The combination of reactance and resistance we call impedance. When the capacitive reactance and the inductive reactance are equal, they kind of cancel each other out, and that's what we call a resonant circuit. That happens at a frequency that we call resonance. So the answer to this question, what happens when inductive and capacitive reactance are equal in a series LC circuit? Resonance causes impedance to be very low. Because at that frequency, the only thing that contributes to the impedance is the resistance of the circuit, which is generally pretty low. The next question asks, what is reactance? Well, reactance is opposition to the flow of alternating current caused by capacitance and inductance. The next question, which of the following is opposition to the flow of alternating current in an inductor? That's just another way of asking the same question. The answer is reactance. The next question says, which of the following is opposition to the flow of alternating current in a capacitor? It's also reactance, specifically capacitive reactance, but the answer choice is just reactance. Next question, how does an inductor react to AC? If you think about an inductor, it's just a coil of wire. Any wire has resistance to it, but as we coil it up, the magnetic field increases the opposition to the current flow, or the reactance. If the frequency is low, it's more like DC, like direct current, and the current has time to reverse direction. The magnetic field that builds up has time to collapse and return the energy to the circuit as the current is reversing direction. So it's not that difficult for the current to flow. But as the frequency increases, it becomes harder for the energy in the magnetic field to collapse back into and supply that energy back to the circuit and cause the current to flow when it's reversing direction. So the answer is, as the frequency of the applied AC increases, the reactance increases. It becomes much more difficult for current to flow in that circuit. The next question asks, how does a capacitor react to AC? It's just the opposite. Capacitors store energy in an electric field, but current doesn't actually pass through the capacitor. It has an insulating layer in between the two plates. So current can flow on either side of the capacitor, and if it's AC, it will alternate back and forth on either side of the capacitor. And as the frequency of the applied AC increases, it still flows easily on either side of that capacitor. So it's actually easier. As the frequency increases, the plates don't fill up completely or discharge completely, so it's actually easier for AC to flow on either side of a capacitor as the frequency increases. So the answer choice, as the frequency of the applied AC increases, the reactance decreases. Remember they're opposites. For inductors, as frequency increases, the reactance gets higher and higher. For capacitors, as the frequency increases, the reactance gets lower and lower. The next question is, what is the term for the inverse of impedance? Just as there is a term for the opposite or the inverse of resistance, which we call conductance, the opposite or inverse of impedance is admittance. The next question says, what is impedance? Well, impedance is a combination of resistance and reactance. So we're going to call that Z. The symbol for impedance is Z. Now remember, from Ohm's law, resistance was voltage divided by current. But if we have a complex circuit that contains both resistance and reactance, so we have impedance, then we'll replace resistance with impedance. And Ohm's law now becomes impedance equals voltage divided by current. So the answer to this question is the ratio of voltage to current. The next question asks, what unit is used to measure reactance? Well, reactance is an opposition to current flow, so we're going to use the ohm, just like we use in resistance. Reactance is measured in ohms. And by the way, impedance is also measured in ohms. The next question says, which of the following devices can be used for impedance matching at radio frequencies? Now, you want your antenna to be at the same impedance as your transmitter. You also have to transmit that power from the transmitter to the antenna over a distance, so there's going to be a feed line. So you want the impedance of your transmitter to match the impedance of your feed line, which matches the impedance of your antenna. Now, if those don't all match, you can adjust the impedance in several different ways. One is by using a transformer. Another method is to use a pi network. That's a combination of capacitors and inductors. And so you can adjust the impedance by adjusting the reactance of either the capacitors or the inductors or both. A third option is by using a length of transmission line. If you think about it, a transmission line acts like, in some ways, a capacitor. Like a coax has a center conductor separated from an outer shield, another conductor, by a certain space. That's exactly what a capacitor is. Two conductors separated by an insulator. Even a ladder line, two conductors separated by a distance between them, that's a capacitor. So by using a length of transmission line, you can also adjust the impedance. So the correct answer for this question is all of the choices are correct. The next question asks, what letter is used to represent reactance? Reactance is represented by the letter X. The last question is, what occurs in an LC circuit at resonance? Well, at resonance, the inductive reactance and the capacitive reactance cancel each other out, and the only part of impedance left would be the resistance. So you're going to transfer the most power from your transmitter to your antenna at resonance. That ends this question set. I have a link to a wonderful video I made about LC circuits and impedance. You can click on that link in the video if you want to learn more about that. Thanks, and we look forward to seeing you in the next episode. 73, this is KE7CR.